In this video, we're going to cover the production of alcohols, looking at the hydration of alkenes, the fermentation of glucose, and the use of biofuels. The oxidation of alcohols, looking at different kinds of carbonyls, how we can test for carbonyls, different types of alcohols, what oxidation agents are, and ultimately how alcohols can be oxidized. And the dehydration of alcohols, looking at the dehydration mechanism and a special case example of this. We're going to start off by looking at how alcohols can be produced through the hydration method. This involves reacting ethene with water. The reaction is an equilibrium using a phosphoric acid catalyst, which will produce ethanol. The reaction needs to be done at 300 degrees Celsius and at a pressure of about 60 atmospheres. This reaction will give a yield of around 51%. You also need to know the mechanism for this reaction. We'll start off by drawing ethene and drawing a H+ ion which comes from the phosphoric acid catalyst. The first step is similar to what you saw in the electrophilic addition mechanism from the previous topic. The electrons in the double bond attack the H+ ion. This will produce the following carbocation intermediate. And we've then got the water molecule, which was our second reactant. The oxygen on the water will have a lone pair. And this lone pair will then attack the positive carbon. This will give us the following intermediate structure. We've now added the water molecule to the carbon. Oxygen has now got 3 bonds, where it would normally have 2. So it now has a positive charge. Similar to as you saw with nitrogens and hydrogens in nucleophilic substitution, we're now going to lose one of the hydrogens from the oxygen-hydrogen bond by drawing the arrow going from the oxygen-hydrogen bond to the oxygen. This will give us our final product of ethanol, as well as a H+ ion. This is why the phosphoric acid is a catalyst. We use a H+ ion at the start, and that H+ ion is regenerated at the end of the mechanism. Ethanol can also be produced through the fermentation of glucose. In this process, we start off with glucose, C6H6O6. We then add yeast at a temperature of about 30 to 40 degrees, and this is going to be using anaerobic respiration. This then produces the ethanol and carbon dioxide as byproducts. Steam hydrolysis, the method we looked at earlier, requires ethene, which comes from crude oil and is a finite resource. It comes from fossil fuel. This fermentation process uses glucose, and it is another important method of producing methanol, as it doesn't require that fossil fuel starting material. Here we can turn glucose, which we can get from plants, into ethanol. The enzymes in yeast work at an optimum temperature of about 30 to 40 degrees. If it is too cold, the reaction is too slow. If it is too hot, the enzyme is denatured or destroyed. When the solution reaches about 15% ethanol, the yeast dies. So this is the greatest concentration we can make in the reaction solution. We therefore need to use fractional distillation to increase the concentration of the ethanol. Fermentation is cheap and uses renewable resources. However, the fractional distillation step is needed to collect and purify the ethanol. This takes extra time and money. We're now going to compare the processes of hydration and fermentation. Hydration has a very fast rate of reaction. Fermentation is much slower. Hydration produces a pure product as part of the process. In fermentation, you need to further purify that product using fractional distillation. Hydration uses ethene, which is a finite starting material, while fermentation uses glucose, which is a renewable starting material. Hydration is a continuous process. The ethanol can be produced at a continuous rate through the machinery used as part of that process. Fermentation is a batch process. You have to use the yeast with the glucose, wait for it to ferment, and then collect your product at the end. You'll produce your ethanol in a series of different batches at set intervals of time. The continuous process requires expensive equipment. However, this means the labour costs to produce the ethanol this way are quite low. Conversely, in the batch process, you've got quite cheap equipment, but it requires a higher labour cost as lots of people are needed to use the equipment and to produce it this way. Biofuels are made from biological material which has recently died. For example, sugar from sugarcane can be fermented to produce ethanol, which can then be added to petrol. Since these bioethanols are made from a renewable resource, the glucose, they are more sustainable than using fossil fuels. Whilst they still release carbon dioxide when they are burnt, they only release what was absorbed by the plant during its growth. Some consider these to be carbon neutral. There are 3 stages when looking at if a fuel is carbon neutral. The first stage is to look at how it was produced. In this case, photosynthesis was used to produce glucose. This is the equation for photosynthesis, and we can see it takes in 6 molecules of CO2. The next stage is the conversion of glucose to ethanol. This is the fermentation process we looked at earlier on in this video, and we can see it produces 2 molecules of CO2 as a product. The final stage is the combustion of the ethanol fuel. So this is the equation for that combustion, and we can see that it produces 4 molecules of CO2 as a byproduct. So 6 molecules of CO2 were taken in, 2 were produced during the conversion of glucose to ethanol, and 4 were produced during the combustion of the ethanol. So you could argue this process was carbon neutral, as 6 molecules were taken in, used as reactants, and in total 6 molecules were produced as products. So the total amount of carbon dioxide in equaled the total amount of carbon dioxide coming out. However, this doesn't necessarily mean the process is fully carbon neutral. Fossil fuels will need to be used for providing the energy for the machinery used to produce the fertilizers and harvest the crops, to transport the crops, to refine the biofuel, and to then transport the biofuel. There are also some ethical concerns around the use of biofuels. There is what is called the food versus fuel debate. If land is used to produce crops for biofuel, it is not being used to produce food instead. Not enough land to grow the crops leads to deforestation to make room for more land. This in turn destroys habitats and releases large amounts of carbon dioxide into the atmosphere. Lots of fertilizers will also need to be used to grow these crops, which can leach into water sources, destroying habitats. We're now going to recap different carbonyl compounds, aldehydes, ketones and carboxylic acids, what we covered in the first topic, as we're going to be looking at these throughout the remainder of this topic. Aldehydes have the suffix -al and the CHO functional group. So for example, this would be an aldehyde with 3 carbons in its chain. So this is propanal. This aldehyde is slightly more complicated, with 4 carbons in the chain and a methyl group. And in this case, the molecule is 3-methyl-butanal. 4 carbons, therefore butanol. The methyl group is on carbon 3, because the aldehyde group will always be carbon number 1. Ketones have the suffix -one. They have the RCOR functional group. And this would be a simple example of a ketone with 3 carbons in the chain. So this would be propanone. This is a slightly longer ketone. This time we've got 5 carbons in the chain. So this molecule would be pentan-2-one. The 2 to show that the ketone is on the 2nd carbon in the chain. Carboxylic acids have the suffix -oic acid. And the functional group RCOOH. This would be an example of a carboxylic acid with 3 carbons in the chain. So this would be propanoic acid. Again, we have a slightly more complex example. This time there are 2 carboxylic acid groups on the molecule. So this molecule would be propane dioic acid. We're now going to look at the chemical tests for aldehydes and ketones, so how you can tell these 2 chemicals apart. The first test is using Tollens reagent. And this is a colourless solution of silver nitrate dissolved in ammonia. If heated in the presence of an aldehyde, a silver mirror will form. So if you were to do this in a lab, you'd probably get something similar to B. A true silver mirror looks something similar to C. To get the result as shown in image C, you've got to use quite high concentrations of the chemicals, which you might not use yourself in a lab. Ketones do not react with Tollens reagent, therefore you would see the negative result. You can also use Fehling solution to tell them apart. Fehling's is a blue solution of copper 2 ions dissolved in sodium hydroxide. If heated in the presence of an aldehyde, a brick red precipitate is formed. So the blue solution changes brick red, and we can see there's a precipitate formed in there. Ketones do not react, so the solution would stay blue. Just like carbocations, which you looked at in the previous topic, alcohols can be primary, secondary, or tertiary, depending on which carbon atom the hydroxyl group, the alcohol group, the OH group, is bonded to. This would be an example of a primary alcohol, as with just one R group or carbon-base group coming off the carbon on which the OH is attached. This would be a secondary alcohol, as there are two R groups on the carbon where the OH is. And this would be a tertiary alcohol, as there are three R groups on the carbon with which the OH is attached to. We're now going to look at the oxidation of alcohols. To oxidise an alcohol, you need to use an oxidising agent. We'll learn more about what oxidation is in a moment, but if you want to oxidise an alcohol, you'll typically use potassium dichromate. It has the chemical formula K2Cr2O7, and it is typically acidified when you do it in the laboratory. Writing equations with this chemical could be quite complicated, so to simplify this in an equation, we just use an O in square brackets to represent the K2Cr2O7. So you commonly see this written here instead of this. In organic chemistry, oxidation is the process of adding more bonds to oxygen. Depending on the type of alcohol which is being oxidised, aldehydes, ketones, or carboxylic acids can be produced in this process. For example, if we started with a primary alcohol and we distilled the alcohol with acidified potassium dichromate, we would form an aldehyde. We'll have a look at the different conditions of distillation and reflux, which we'll look in a moment, separately. If we then had an aldehyde, which we refluxed with acidified potassium dichromate, we would form a carboxylic acid. Again, we'll look at what distillation and reflux mean later on. If we had a primary alcohol and refluxed that straight away with our oxidising agent, we would go straight to forming a carboxylic acid. We would skip out the formation of the aldehyde. So we can only form the aldehyde when we distill a primary alcohol. If you want to produce the carboxylic acid, you can reflux the primary alcohol from the start. If we have a secondary alcohol, we can use reflux to change a secondary alcohol into a ketone. Again, we'll need to add some of the oxidising agent we looked at a moment ago. Tertiary alcohols cannot be oxidised. We're now going to look at this process again, but this time we're going to look at the displayed formula of these different chemicals so we can see how the number of bonds to oxygen are changing throughout the process. So if we have a primary alcohol and we use distillation with an oxidising agent, we will form an aldehyde. We can see in the reactant, the alcohol, how there was one bond between carbon and oxygen, and now there are two, meeting our definition of oxidation as adding bonds to oxygen. If we were to reflux that aldehyde, we would turn it into a carboxylic acid. The H group here is now an OH group. If we were to do reflux on the primary alcohol, we could change it straight into a carboxylic acid. If we have got a secondary alcohol and we reflux it, we can change it into a ketone. We should hopefully now see why primary alcohols formed aldehydes, because they've got a hydrogen group at the end and they lose a hydrogen, and why secondary alcohols form ketones, because they've got a carbon at each end, and when they lose the hydrogen for the extra bond to oxygen, there is now a carbon at each end, meaning we've got a ketone compared to an aldehyde. This also shows us why we can't change a ketone into a carboxylic acid, because there is no hydrogen which can be lost to attach an OH group. We can't break either of these carbon-carbon bonds here or here, so there's nowhere else to add the OH group to. This also shows us why tertiary alcohols cannot be oxidised. There are no hydrogens on the carbons to be lost, therefore there's no way to add an additional bond to oxygen on this molecule. When writing equations, we use the O in square brackets to represent the oxidising agent. So in this case, a primary alcohol reacts with one oxidizing agent to form an aldehyde and a molecule of H2O. The H2O is here to balance the equation. If we think about it, we've used an oxygen from the oxidizing agent, which hasn't ended up in our final product, so that's where this oxygen comes from, because we can treat our oxidizing agent as just being an atom of oxygen added to our reactant. We've lost a hydrogen of the oxygen and a hydrogen from the carbon, where the two H's come from, therefore a molecule of water is produced. If we take that aldehyde and react it with another oxidizing agent, we would then form a carboxylic acid. This time, there is no water present, as essentially we're just adding this oxygen to where this bond here is, forming the OH. There are no mechanisms to learn for this process, so we don't need to worry about how this actually happens. We just need to be confident with the equations that we're using. We know that if we use reflux on a primary alcohol, we can go straight from a primary alcohol into a carboxylic acid. In this case, we combine the previous two equations. So we're doing two steps of oxidation. We're going to the aldehyde, then to the carboxylic acid. So we need two equivalents of the oxidizing agent, and we're going to produce the molecule of water, which would have been formed in the first step. Finally, if a secondary alcohol reacts with an oxidizing agent, it will produce a ketone and a molecule of water. We're now going to look at a couple of example questions you might be asked about oxidation. Ethanol can be oxidized to ethanal under distillation conditions. So let's write the equation for that process. As you can see, we've got ethanol plus one oxidizing agent, because we know ethanol to ethanal, the alcohol to the aldehyde is just one step. So we're going to form ethanal and water. And we can check the equation is balanced because we just treat the O in square brackets as an oxygen atom. So there's the same number of atoms on each side of the equation. This time, we're asked to write the equation for when ethanol can be oxidized to ethanoic acid under reflux conditions. This would be our equation, as we know that going from ethanol to ethanoic acid, or an alcohol to a carboxylic acid, is two jumps. Therefore, we're going to need two lots of our oxidizing agent, and we're going to form the ethanoic acid and the water. If you're unsure how we knew which products to form, look at the general examples we had on a minute ago, and they'll be the same for any given alcohol. You just need to identify whether it's primary, secondary, or tertiary, and how many series of oxidations you are doing. Finally, propan-2-ol can be oxidized to propanone under reflux conditions. This is a quite straightforward equation looking at the formation of a ketone. So we would have our propan-2-ol with one equivalent of oxidizing agent, because we know that a secondary alcohol can only be oxidized once to a ketone, forming our ketone and water. This is a diagram showing distillation. You can watch the separate video on practical techniques for the methods and common errors with this practical, but distillation is where you heat a substance in a controlled manner. As you heat the substance, either using a Bunsen burner or a hot plate for example, the solution you're heating, if it starts to evaporate, turn into a gas, will travel up the glassware, through the condenser to a collection unit. The condenser is a cooled piece of equipment where water comes in the bottom of the condenser and out of the top, keeping it cold, which condenses the reaction product. We'd use this in oxidation, for example, because if we wanted to turn an alcohol into an aldehyde, we want to remove the aldehyde as soon as it is formed. We don't want the aldehyde to stay in the reaction mixture so it can be oxidized further into a carboxylic acid. This way, as we're heating up our alcohol and our oxidizing agent, as soon as the aldehyde is formed, it will evaporate, travel down the condenser, where it will turn back into a liquid, will be condensed, and we can collect the aldehyde here. This is the equipment set up for reflux. This time we have the condenser being vertical in our heating solution. Reflux is used to heat a chemical for a prolonged period of time without losing any of the reactants. In this case, if for example we were wanting to oxidize a secondary alcohol into a ketone, or a primary alcohol straight to a carboxylic acid, we would heat the chemical in here with our oxidizing agent. Whilst it is being heated, if any of the chemical was to evaporate, it would travel up the condenser, where it would be cooled by the water entering, causing it to condense back to a liquid and be returned back to the reaction mixture. This way, none of the solution which we heat will be evaporated and lost. If it evaporates, it'll condense and return, allowing for the solution to be heated for a prolonged period of time. This heating is necessary to turn a secondary alcohol into a ketone. In the case of going from a primary alcohol to a carboxylic acid, as soon as the primary alcohol forms the aldehyde will evaporate, be returned, and further oxidized into a carboxylic acid. We're now going to look at the process of dehydrating alcohols. When an alcohol is dehydrated, it means we're turning it into an alkene. Dehydrating alcohols allows for the production of alkenes through renewable sources. For example, ethanol can be produced through the fermentation of glucose and then dehydrated to form ethene. Alkenes are important chemicals in the production of polymers. Dehydration of unsymmetrical alcohols can result in more than one product, because the double bond can go on either side of the carbon that had the OH group on it, and we'll look at the mechanism in a moment. The product of this reaction is usually in a mixture with water and acid, so the alkene will need to be separated through distillation. We're now going to look at the mechanism for this process. Ethanol is reacted with a sulfuric acid catalyst to produce ethene and water. We'll start off by drawing ethanol and a H+ ion. The H+ ion comes from the sulfuric acid catalyst. In the first step of the mechanism, a lone pair on the oxygen attacks the hydrogen ion. This makes a new bond between the oxygen and the hydrogen. The oxygen now has 3 bonds, where it would normally 2, giving it a positive charge. The positively charged oxygen pulls electrons away from the carbon, so the H2O molecule on the end leaves, so the carbon-oxygen bond is broken. This forms an unstable carbocation intermediate. So the carbocation intermediate loses a H+. This will form an alkene, giving each carbon the correct number of bonds. So we can see here our alkene is formed. The H, which is lost, is the H+ from the start. Therefore, we've regenerated the H+, therefore it is a catalyst. There is a special case of this reaction you need to be aware of. Let's look at this molecule here and see what would happen during the dehydration process. So we would have our H+ ion, and the first step would occur exactly like we looked at a moment ago. The lone pair on the oxygen would attack the H+. This intermediate would be formed, and the water molecule would be lost. And this would be our carbocation intermediate formed. However, there isn't another hydrogen which can be lost. We've got a methyl group, a second methyl group, and a bromine. Neither of these 3 atoms directly bonded to the second carbon are hydrogens, therefore none of these can be lost to form the double bond in the middle. Therefore, this reaction can't take place. So this would be an example of an alcohol which can't be dehydrated because the carbon adjacent to the carbon with the OH doesn't have a hydrogen attached, therefore the final step of the mechanism wouldn't be able to take place. It's worth being aware of this because sometimes exam questions will ask you to identify a molecule which can't be dehydrated.